Good, good. All right. Good morning. We will have this very important session this morning of thesis presentations. We have 6 presentations, and each presentation will be for 15 minutes each, followed by 5 minutes of discussion. And it will be strictly within that, no extending time. And at the end of it, there will be a best thesis chosen from it. So we'll get started with Parthapratim Goswami on chemical abundances of metal poor stars as probes of neutron capture nucleosynthesis. Parthapratim.
Hello. Thank you, sir. Am I audible? Yeah, okay. Good morning, everyone. I am Parthapratim Goswami. I did my PhD from the Indian Institute of Astrophysics under the supervision of Professor Aruna Goswami. As you can see, I will be talking about chemical abundances of metal poor stars as probes of neutron capture nucleosynthesis. This is my thesis title. The main results of the thesis have been presented in these 8 papers. As the title suggests, my thesis is primarily aimed at understanding a very fundamental physics problem, that is neutron capture nucleosynthesis. And we attempted to understand neutron capture nucleosynthesis by studying the chemical composition of metal poor stars. So first, I'll briefly discuss what neutron capture nucleosynthesis is, and then I'll go to metal poor stars. We know that the elements up to iron are produced by fusion, and the elements which are heavier than iron, it is not working, which are heavier than iron cannot be produced by fusion. These elements are produced by neutron capture nucleosynthesis. Classically, there are 2 known neutron capture processes. One is S process or slow neutron capture process. The other one is R process or rapid neutron capture process. As the names imply, for S process, the neutron capture time scale is much longer than beta decay time scale. And for R process, the neutron capture time scale is much shorter than beta decay time scale. For R process, the required neutron density is around 10 to the power 15 times more than that of S process. And the proposed sites for both the processes are also different. For S process, the proposed sites are low and intermediate mass AGB stars. And for R process, the proposed sites are supernovae and neutron star mergers. It is not working. Oh, okay. So we come to metal poor stars now. Here I have shown 2 sample spectra. The yellow one is the spectrum of the sun, and the red one is the spectrum of one of our program stars. And we can clearly see the difference between the number of lines and the strength of lines in both the spectra, because the metal content of our program star is 1,000 times less than that of the sun. So these are metal poor stars, and metal poor stars are population 2 stars, which are formed from the ejecta of the first stars in the universe. So they carry the imprints of the early universe, and by studying the chemical composition of metal poor stars, among many other things, we can trace back the origin of neutron capture elements and their production sites. Because a large fraction of metal poor stars, such as barium stars, CH stars, and carbon-enhanced metal poor stars, exhibit enhanced abundances of heavy elements in their atmosphere. By the term heavy elements, I mean the elements which are heavier than iron. For this work, we have selected our program stars from several metal poor star catalogs in the literature. We have acquired high-resolution spectra of the program stars using different telescopes across the globe. We have used the radiative transfer code MOOG to analyze our spectra. We have taken our atmospheric models from the Kourous grid of model atmospheres. We have derived the atmospheric parameters of the program stars. We derived the abundances of 24 to 30 elements of each program stars. So based on the elemental abundances, we have classified our program stars into several metal poor star categories. We have found 1 normal metal poor star, 5 barium stars, 1 CH star, 6 Camp S stars, 3 Camp RS stars, 3 extremely metal poor stars, and a star which is a very unique star that I'm going to discuss in our upcoming slides. So the first highlight of the work is we have performed first-time detailed high-resolution spectroscopic analysis of 20 metal poor stars. A major portion of the thesis has been dedicated to the study of carbon-enhanced metal poor stars, or CAMP stars. This is a very interesting class of objects. Based on the enhancement of neutron capture elements, CAMP stars are classified into 4 subgroups. In CAMP no stars, heavy elements are not enhanced. In CAMP S stars, S-process elements like barium is enhanced. In CAMP R stars, R-process elements like europium is enhanced. And in CAMP RS stars, both S and R process elements are enhanced. So this subclass of CAMP stars draws special attention because I have already discussed that S and R process elements are produced in completely different stellar environments with different physical conditions. But these stars are carrying both S and R process elements. In our thesis, we have mainly focused on the study of CAMP S and CAMP RS stars. As the first project, we tried to understand the formation scenarios of CAMP S and CAMP RS stars in context to the program stars that we have. This is the formation scenario for CAMP S stars. Let us consider a binary system. Here one star is slightly massive than the other one. So the slightly massive star will evolve faster. It will evolve to AGB phase. AGB phase is the end phase of stellar evolution for low and intermediate mass stars. And in the AGB phase, a star can produce S-process elements and carbon. And in the AGB phase, the star loses its envelope. And during that process, it gives S-process elements to the companion. Now the companion star becomes an S-process enriched star. And after the AGB phase is over, a white dwarf remains. This is the most widely accepted formation scenario for the formation of barium stars, CH stars, and CAMP S stars. Because all these stars are enhanced in S-process elements, and all these stars are found in binary systems with an invisible companion, which is a white dwarf. Now we come to the formation of CAMP RS stars. I have already discussed that CAMP RS stars contain both S and R process elements. So there are several scenarios proposed for the formation of CAMP RS stars without any conclusive evidences. In this paper, we have discussed all those scenarios in context to our program stars, and we found that none of the scenarios can explain the abundance peculiarities of the CAMP RS stars that we have studied. Because in all these scenarios, it is considered that S and R process are produced in different stellar sites, and somehow they come to the star that we are observing as a CAMP RS star now. But there is a tight correlation between S process elements and R process elements. And this correlation is found for both CAMP S and CAMP RS stars. This correlation of S and R process elements cannot be explained if it is considered that S and R process elements are produced in different stellar sites. Therefore, an intermediate process or I process has recently been suggested, which can produce both S and R process elements in a single stellar site. Now, this I process is intermediate in the sense that the required neutron density is intermediate to that of S process and R process. In S process, the required neutron density was 10 to the power 7 to 10 newtons per centimeter cube. In R process, the required neutron density was 10 to the power 20 to 25 newtons per centimeter cube. But for I process, the required neutron density is 10 to the power 12 to 15 newtons per centimeter cube. And there are several proposed sites for I process as well. But the one which has got more confidence over the last few years is the low and intermediate mass AGB stars, similar to that of S process. Then we tried to see whether I process can explain the abundance peculiarities of our Camp RS stars, whether I process models can reproduce the observed abundance patterns of our Camp RS stars. And we used the I process yields from Hampel et al. 2016. And we extended the study to 8 more Camp RS stars found in the literature for which the production channels were not studied. We found that I process models with neutron densities of around 10 to the power 12 to 15 newtons per centimeter cube can reproduce the observed abundance patterns of our Camp RS stars very well. So this is the second highlight of our thesis. We have confirmed the recent claims that I process is responsible for the formation of Camp RS stars. Our project 2 is motivated by an outlier, HD 145777, which could not be classified into Camp S or Camp RS groups by any of the existing classification schemes. Some classification criteria put this object into Camp S group, some classification criteria put this object into Camp RS group. So this object compelled us to revisit the classification schemes of Camp S and Camp RS stars. We have critically examined all the existing classification schemes of Camp S and Camp RS stars. Here I have shown 2 of them. This is the first classification criteria given by Beers and Christlip 2005. This is based on barium by europium. And this is the recent classification criteria given by Hansen et al. 2019. This is based on strontium by barium. Now, here the red grid is the region defined for Camp RS stars by the respective classification schemes, and the black grid is the region defined for Camp S stars. We can see that the stars are everywhere. So these classification schemes cannot distinguish Camp S and Camp RS stars. So we have put forward a new classification scheme based on the abundances of barium, lanthanum, and europium. Here the red grid is the region defined for Camp RS stars, and the stars which fall in this black grid region, we have to look for europium abundance for those stars to classify them as Camp S or Camp RS. And we found that this classification criteria can distinguish Camp S and Camp RS stars very well. So this is our third highlight of the thesis. We have put forward a new classification scheme based on barium, lanthanum, and europium to distinguish Camp S and Camp RS stars. Our third project is about a very peculiar star that we have discovered. This is HE1005-1439. This is a first of its kind object, and this is an extremely metal poor star with metallicity minus 3.03. We classified this object based on our classification scheme, and this is a Camp S star according to our classification scheme. But the ratio of heavy S process elements to light S process elements of the star is very close to that of Camp RS stars. So we tried to see whether S process models or I process models can explain the abundance patterns of the star. We found that neither S process nor I process can reproduce the observed abundance pattern of the star very well. But a combination of S and I process with similar contributions from both the processes can reproduce the observed abundance pattern of the star. So this star contains 56% S process contributions and 44% I process contribution. So this object forms a new class of objects with a distinct abundance pattern that has never been observed before. We proposed a formation scenario for this object involving a binary picture where in the AGB star, S and I process can operate one after the other, and it pollutes this star that we found as camp IS star now. And this object is expected to reveal many unknown details about this AGB evolution. So this is our fourth highlight of the work. We have identified a new site where S and I process operate in succession. Our fourth project is about barium stars. Barium stars are slightly metal-rich than camp S stars. Barium stars are also S process enhanced. So depending on the enhancement of S process elements, barium stars are classified into mild barium stars and strong barium stars. Although it is known that both mild and strong barium stars are produced through the same AGB mass transfer scenario, but it is not known how they get such different levels of enhancement. We derived the mass distribution of the barium stars, and we found that mild and strong barium stars occupy the same mass range. Then we derived the mass distributions of the progenitor AGBs of the barium stars, and to the best of our knowledge, this is the first attempt to do so. And we found that progenitor mass distributions of mild and strong barium stars peak at different values. So we propose that the initial masses of the progenitor AGBs of barium stars dominantly control the formation of mild and strong barium stars. This is the last highlight of the thesis. We have derived the mass distributions of the progenitor AGBs of barium stars and found different mass distributions for the progenitors of mild and strong barium stars. I have already highlighted the main achievements of the thesis. Let me end my talk with a take-home message for those people who are not from this particular field. This is a picture that I painted for my thesis. This was an idea till 2014. It was considered till 2014 that heavy elements, the neutron capture elements, are produced through S and R processes. But our current understanding of the galactic chemical evolution says that I process also contributes to the galactic chemical evolution. Thank you.
Thank you, Parthapratim. Questions, please. Arnab.
So you showed a plot showing in the metal poor stars the correlation between R process products and S process products, and then you said that since these two processes take place in different astrophysical scenarios, you rather proposed an I process, and I don't know the details of I process, but with that I process, can you explain this correlation between R process products and S process products?
We have a more updated version of that plot. Let me show you. It will come here. Yes. So here you can see that this is the black stars are camp S stars, as process enriched, and the red stars are I process enriched. And the correlation is the same correlation from the camp S region to camp RS region. So it may not be different processes. That's what I feel, that S process and I process may not be very different because they are found in AGB stars. So this object that I explained, which contains both S and I process products, can explain this trend. If we find more such objects, we can explain this trend coming from S process. So we don't know how exactly AGB star produces S process elements and I process elements. This interplay between S and I process elements is not studied well. It is not known. And these kinds of stars can constrain the theoretical models to study this aspect.
Yeah, this is a good talk. I just was wondering, these are all very metal poor stars. That means very low mass stars.
Excuse me, sir?
Metal poor stars.
Yeah.
They must be very low mass stars, no?
These are low mass stars.
And these are all highly evolved stars, like AGBs and things
Yes.
like that. So where do we get the neutron densities for both R process and S process?
Where do we get?
Neutron, source for the neutrons.
Yes, it is in the AGB. So the stars that we are observing, they are not in the AGB phase. The stars that we find as Camp S or Camp RS, they are not in the AGB phase. They are giants, but their companions produced those elements, and through mass transfer, they give the elements to the star that we are observing as a Camp S or Camp RS star now. So these elements were produced in the companion, which was an AGB much longer.
Yeah, nice talk, Partho. I have two questions. One is, again, follow-up of what Arunabh was asking. So can you also comment on if there are two processes which contribute to, you are saying I process should be unique, not to R and S to contribute to the the CMP R plus S stars. So in terms of numbers,
IS or RS?
yeah, so you have said you are invoking CMP I process, right?
Yes.
Because there are two processes in entirely different sites couldn't contribute to this.
Yes.
So just to, in terms of numbers, like if there are two process, like if you have purely CMPS and purely CMPR, and also comparing the CMPR plus S, the numbers, in terms of numbers, how does they go? Can you comment on that?
I think
Which is the dominant one?
Camp S and Camp RS or Camp I,
Yes.
now this is called Camp I because you are saying Camp R plus S, there is a different class of objects that they have found as Camp R plus S, where R process elements come from different side, S process comes from, that is not I process.
Yes.
So this is now Camp I. So Camp I and Camp S are like similar in numbers.
Okay.
They're
So Camp R is
Camp
much
R
fewer.
is much fewer.
Okay, okay. Another question is just the metallicity dependence of I process, like how does?
Metallicity dependence of I process has not yet been studied very well.
Okay, thank you.
Okay, last question.
Yeah, nice talk, Partho. I just have one question regarding the, are all these stars in binary always?
They say the 80, like long-term variation, long-term radial velocity monitoring, we didn't do, but who did those things, they claim that 80% of these stars are in binary, but the stars which are not found in binary, they say they maybe the periods are much longer than they observed, or maybe the plane of inclination was different, so they could not find. It is believed that all the stars are in binary.
So if process is only through binary mass transfer?
Yes,
there is
yes.
no other- okay.
Thank you, Partho Pratim.
Thank you, sir.
We will move on to the next presentation by Meera Nandakumar. Study of structure and dynamics of the interstellar medium in nearby spiral galaxies.
Hi, I am Meera Nandakumar. I am a research associate working here in IISc Bangalore, and I completed my PhD from IIT BHU Varanasi. So in my thesis, basically what I was trying to do is understanding the structure and dynamics of the interstellar medium in nearby spiral galaxies. So why spiral galaxies? So well, these are dynamically very active system where a number of processes are happening at large length scales, which eventually result in the formation of different interesting structures that we see in these galaxies. So one of such interesting phenomena that yet need to understand in these galaxies are compressible turbulence in the interstellar medium. So well, from various observational studies, it is an established thing that the ISM is a heavily turbulent medium where we can see scale invariant structures in the density and velocity of the gas. Being a random process, we basically use 2-point statistical quantities like power spectrum to quantify these structures. And this power spectrum is just the Fourier transform of the autocorrelation function. And this is just an example of one of such spatial power spectrum that has been obtained from observations of atomic hydrogen, which is also called H1 21 centimeter observations from our galaxy Milky Way. As you can see, it is obeying a very nice power law which is expected for turbulent generated structures, because compressible turbulence leads to the hierarchical formation of structures through which energy cascade down from large length scale to small scales. By inferring the amplitude and the slope of this power spectrum, one will get clue on the information of generating mechanism of turbulence in ISM. Such numerous attempts have been done in literatures previously, especially at smaller scale, at sub-parsec scale, where people have seen that these structures are attributed to shock-dominated turbulence, which means that the primary driving factor that drive turbulence there is the various stellar feedback like supernova. On the other hand, if we go to larger scale at the size of the galaxies itself, which is of few kiloparsec, there also people So as I was saying, on the larger scales of few kiloparsec also, people have seen this similar power spectrum or power spectrum obeying power law features from the H1 intensity power spectrum estimations for several spiral galaxies. So the question that arising here is, what is the driving mechanism? Will the same supernova is the factor or something else? And the possible candidates that are listed in or that are discussed in literatures for this driving mechanism are gravitational instability, shear from galactic rotation, stellar feedback, etc. So to validate this, we need observational evidence, which is not there. And this is the motivation, or this is one of our motivation to do this work, where one of the objective of this thesis to understand the large scale turbulence and its generating mechanism in external spiral galaxies from observation. And to do that, we need H1 21 centimeter observation, which can be conducted by radio interferometers. So unlike other telescopes, radio interferometers measures a quantity called visibility, which is the Fourier transform of the intensity of the sky that we are observing, which is sampled at discrete points in the observation plane, which something look like this. And this incomplete sampling unfortunately make the direct deconvolution to obtain the true intensity of the sky impossible, and we rely on various deconvolution algorithms which basically generate the best representation of the reconstructed or the best representation of the true sky that we are looking at. And 1-point statistics like large scale profile can be easily estimated or can be reliably estimated from these images. But on the other hand, if you are looking at 2-point statistics like power spectrum estimation, there is a problem. And that is what we have done here. So what we did is, we checked the efficacy of this reconstructed images in estimating power spectra, where we simulated a model galaxy whose power spectrum is well known, which is plotted here as black line here. This is our reference power spectrum to compare with. Then we simulated radio interferometric observation and obtained the visibilities and estimate the power spectrum in 2 ways. One is the conventional way of estimating power spectrum from the reconstructed image, which is image based power spectrum, and the second one is, instead of doing a reconstruction, we measure the power spectrum in the visibility domain itself, which is visibility based power spectrum. And both of them are compared with the model power spectrum here. If you notice, this is the visibility based power spectrum, ash pentagon, which is nicely following the model power spectrum we have in the input. On the other hand, the image based power spectrum is not following, which is telling you that if the science case is to look at 2-point statistical case, then we need to rely on visibility based estimation. And this is a very interesting result, because as the radio astronomy community is entering to the new era of SK, where the radio interferometric observations are planning in such a way that instantaneous reduction of observed visibilities is happening, and on the such hand, during the observation itself you will get the reconstructed image. And this investigation is highlighting a problem that can arise in such scenario, especially in science cases when you are dealing with 2-point statistics. So based on this, we developed a new estimator to measure the H1 column density and the line of sight velocity power spectrum from 21 centimeter observation on external spiral galaxies. So I will not go to the details of this, but the basic idea is following. So from H1 21 centimeter observation, we will get two information. One is the column density of the H1 and the other one is the velocity of the H1. And this can be extracted out by taking the first 0th and the second moment of the intensity maps, and this is the convention generally used. And we use the same technique or similar method, but in the visibility domain. We generate the moments in visibility domain, and from there we extract out the H1 column density power spectrum and line of sight velocity power spectrum of H1. That is what this visibility moment power spectrum estimator does. And we start with 2 galaxies to implement our estimator, NGC 6946 and 5236, which are observed by VLA and UGMRT. And this is the final result. So left hand side is the H1 column density and right hand side is the velocity power spectrum of NGC 5236 galaxy, and this is plotted as a function of inverse of the length scale. And this is the same for galaxy NGC 6946. So in both of these power spectrum, for the 2 galaxy, you can clearly see that it is obeying a nice power law, which is starting from around 11 kiloparsec to 300 parsec for 5236 galaxy, and from 5 kiloparsec to 160 parsec to 5 kiloparsec to 160 parsec in 6946. So measuring this large scale turbulence from observation has been done for first time for any external spiral galaxy. And we infer the slope of this power spectrum, and based on that we conclude that for NGC 5236, the possible driving factor that drives this large scale turbulence is gravitational instability or self-gravity, whereas for NGC 6946, we see the presence of a combination, of compressive and solenoidal force, where the compressive force is coming from gravity and the solenoidal force is possibly coming from magnetic field contribution or shear. So this is again an interesting thing that we need to further proceed, because irrespective of the similar inertial range of cascade and injection scale, the generating mechanism is quite different, and this is highlighting the necessity to highlighting the necessity to measure this, conduct these similar experiments on a large number of galaxies to understand the universal picture. Yeah. So once we have a way to quantify this measurement and get some idea about what is happening, the next question or the ultimate question that we need to ask is how it is affecting the star formation, how this large scale turbulence affect the star formation. For that we investigate how H1 turbulence play a role in the H1 instability. In the H1 instability. For that basically we did a 2 fluid disk stability analysis to measure the Tumre criteria, which will give you idea about instability in the disk. where we incorporate the effect of turbulence also. And what we did is we generate two-dimensional map of this QT, Tumbre criteria, in the different resolution on the galactic disk, and try to see whether any unstable regions are present. And for this analysis, we consider 3 galaxies in our sample, whose various observations have been obtained from archival, multi-wavelength observations have been obtained from archival data. Yeah, so this is just one of such example for galaxy NGC 5236, where the two-dimensional density plot of the QT map has been estimated in the galactic coordinates. And as you can see, these contours are the regions where we probe the unstable regions in this. As you can see, most of these are located or populated along the spiral arms. And we are able to see similar unstable regions in other 2 galaxies also. And we try to did a correlative analysis where try to see how much is the star formation in this region and how it is related, etc. And our final findings are following. We have 3 galaxies here, where for NGC 5236 and 4736, we see that there are unstable regions, and these unstable regions are highly associated with high star formation rate. Whereas for the case of NGC 3351, even though we have unstable region, their respective star formation rate is not high. And even if you look at the cumulative star formation indication for this galaxy 3351, it is also comparatively less compared to other 2 galaxies. Interestingly, in this galaxy, from the column density power spectrum estimation, the slope is sort of telling you that the presence of turbulence is sort of insignificant in this NGC 3351 galaxy comparing to other 2 galaxies. So this is again telling you that even though instability happen, the further fragmentation to happen, which eventually lead to the formation of stars, we need the presence of turbulence. Yeah. So far I was telling about the turbulence generated structures, which are mostly isotropic in the galactic disk. Apart from that, these galaxies are very much enriched with various anisotropic fluctuations also. One of such phenomena which leads to these anisotropic fluctuations in the galaxies are called bending waves, which are not much explored through observations. And this is the second part of our thesis. Yeah. So what is bending wave? So when we have a galaxy and which is undergoing a tidal interaction with nearby satellite galaxies or neighbor galaxies, that will lead to the global bending of the entire disk. That global bending can be easily visible because that bending will create some wavy structure along the velocity along the vertical direction, which can be easily visible through photometry or through density distribution in edge-on galaxy. But these galaxies are limited in number, and because of that also this phenomena has been rarely seen through observation. On the other hand, in this demonstration, what we are saying is that when the bending is happening in the H1 disk, this induces oscillations in both column density and line of sight velocity, where we can see oscillatory patterns in column density and line of sight. And irrespective of the inclination, we will be, okay, I'll just take 1 minute. Yeah, we will see these oscillations in velocity structures very easily. So we conduct a study to probe these structures by doing quantifying harmonic decompositions in the H1 density and velocity structures. And what we see that we choose 6 galaxies, and in all 6 galaxies we see the evidence for bending waves through H1 observations. By this I will just summarize. We basically try to do a groundwork to establish a methodology to probe turbulence in external spiral galaxies, and we successfully probe it, and we also observationally see evidence for bending waves in H1 disks. Thank you.
Yes. Questions, please. Arnab.
Okay, so if a galaxy has a companion, then we know that it produces a bending, but you were talking about bending waves. Is there any evidence that this bending is not just some simple bending, but it's an oscillatory type, and its period must be enormous if there is any wave of that kind? Then I'm very surprised that you can detect it at all. So do you know if there is evidence that it's really a wave, or what is expected to be its period?
So people have seen these this oscillatory structures. Can you just tell me again? I did not completely understand.
No, it gets bent, but I thought that it would just get bent and may stay there. So is there evidence that it's after bending it doesn't just stay there, but it oscillates, or there is a wave, and can one estimate what will be the period of the wave?
So, period from this what we can do is this is a mixture of different modes of waves. So by detecting each modes, from that we can sort of see what is the wavelength and all, whether it will extend out, whether it will dice out at the extent of the disk, I am not sure.
Hi, I just wanted to ask you a question regarding, since you were talking about compressive turbulence, what are the typical ranges of turbulent Mach numbers you are thinking about? And the other question is, later at some point you were talking about using a model galaxy, and from there you are kind of forward modeling your observable, like 21 centimeter, right? So can you elaborate on what kind of model galaxies you are talking about? So the reason I'm asking this is, I'm just curious about the kind of model. For example, there are simulations, right? Like, for example, the Agora simulations where you have lots of disk structures, like disk galaxies. And then if you do the same kind of synthetic observables and find out what kind of power spectrum do you get, and then you'll perhaps know that if you make the observations, and in the synthetic observations, how reliable is it? Because you also know the field of the galaxies, and from there, if you do the similar procedure, and how the simulations and the result that you obtain from synthetic observations match. So in that sense, I just wanted to know the model of the galaxy that
So
you are looking at.
you meant what is the type of galaxy we have considered?
Yes, the model.
Yeah. So we have here consider thin disk galaxies, because that is going to be one of the assumption in our estimator. And also to start with, we only consider very simple galaxy where the rotation curve is very smooth, so that we don't have other complications of this warping or things like that. We have just considered that. That I did not check.
Yeah, so hello. So I just want to know that how did you make an interpretation that having different drive here of like in two different galaxies, you get the same injection scale? Is that not surprising?
Yeah, this is something interesting. Like we get so one of the caveat here is that so yeah, so these are like primary findings only, like in the sense that so we compare this with the numerical simulations by Federer et al., where they have two type of forcing, compressive and solenoidal, and if you see that the velocity slopes are not that much different. On the other hand, we have a slight distinguishability in the density slope. So based on that, we say that like there is a combination of compressive and solenoidal. Yeah, so there are many things that comes into factor that we need to again check and see, basically.
I don't see any more hands up. Thank you very much. Yeah. So move on to the next presentation by she's going to talk about probing the star formation activities of galaxies residing in voids and filaments using astrocytes.
Okay. Good morning, everyone. Today I am going to present my thesis work titled Probing Star Formation Activities in Galaxies Residing in Voids and Filaments. I am presently a postdoc at Aries, Nainital, and I have completed my thesis work at NIT Rourkela in collaboration with Ayuka Pune. So, the outline of my talk is as follows. I'll start with the introduction. So, basically the cosmological principles that governs our universe says that the universe is isotropic and homogeneous. But if we zoom into the cosmic web and look at the scales, megaparsec scales, at the scales of galaxy clusters, we start to see some inhomogeneity in the web in the form of voids, clusters, filaments, and this inhomogeneity is visible in voids, in simulations as well as observations. Now, so these components, these cosmic web components have different evolution history, and they have different characteristic parameters such as their mass fraction, volume fraction, as well as the environment density. So, wherein the cluster has the highest environment density, followed by filaments and voids. So, these large scale structures where the galaxy reside, they leave some imprint on the characteristic property of these galaxies, and these galaxy observables could be their morphology, color, star formation rate, etc. Now, from what that has been reported in the literature, if we look at the impact of density, environment density on the colors of galaxy, the low mass galaxies have in secular or in underdense environment are usually blue, and as the density increases, their color, we get more red galaxies. But at the highest stellar mass end, regardless of the environment, we are likely to get red galaxies in the cosmic web. But there are certain exceptions to it, which I will be highlighting in my thesis in the following presentation. And similarly, with stellar mass also, we have seen that at high stellar mass ranges, elliptical and spheroidal galaxies, elliptical and lenticular galaxies dominate the system, whereas at low mass end, we get mostly disk, spirals and irregulars. And same effect can be seen for density as well. The motive and objective of my talk is to find out UV counterparts of filaments and void galaxies. We are focusing on UV because it traces recent star formation in the galaxy up to a time scale of 100 mega years, and then once we have the UV counterparts, we want to study their star formation history, their mass assembly, and we want to understand the impact of interaction on the evolution of galaxy, and lastly we want to unwind the effect of environment and mass quenching mechanisms on galaxies. I have primarily used UVIT, which is onboard AstroSat, which is India's first dedicated multi-wavelength observatory, and my observation is done in two filters, one for FUV and the other for NUV. This is the detail of my observations. These were proposed observation, so if we see the red dotted circle here, it indicates Booty's void, which is the largest void in the northern hemisphere, and we also targeted a filamentary structure just beside the void with AstroSat, and these two, the pink and green line shows the line of sight of our AstroSat filament observation, whereas the Booty's void, this blue line shows the line of sight of our observation for the Booty's void. I'll start with the void observation first. Once we get the data from AstroSat, we did data reduction, and then we did some basic steps such as PSF modeling, sky estimation, source detection, and of all the sources that we detected, we were particularly interested in galaxies, so we had to do some classification, and we did some color classification, and we also considered the optical cluster of these galaxies, and in the end we ended up with and for spectroscopy we relied on STSS. So we ended up with 8 galaxies with spectroscopic observation, whereas 159 galaxies didn't had a spectroscopic observation. And one more important thing for our study is the redshift range of these galaxies, because Booty's void lies in the redshift range of 0.04 to 0.06. So out of all the galaxies with spectroscopic redshift, we could only get 2 of 8 galaxies in the Booty's void, and for the remaining, what we did was we calculated our own photometric redshift using EASY. And then we applied some criteria, that is the probability of these galaxies falling in the redshift range of the Booty's void should be greater than 50%, and in the end we end up with 4 of these 159 galaxies which were falling in this range. So we wanted to compare the UVIT versus GALAX observation of these galaxies. So the first row in this figure shows STS's observation of these 4 galaxies followed by UVIT, and we have written their SNR over here below the images, and the last row is the GALAX. So what we see is 3 of these 4 galaxies were newly observed with UVIT. And then we did a basic color magnitude plot for these galaxies, and we found that most of the void galaxies we detect were faint in luminosity and also belonging to the blue cloud. Then these background, the gray dots over here are a random sample in the local universe in the same redshift as the void galaxies, and we did a statistical test over the color distribution of void galaxies and the blue sequence of a random sample of galaxy chosen, and we found that these two populations are statistically different, which tells us about the impact of environment on galaxies. So and then so in the second part of my work, I was interested in studying this high stellar mass galaxy in the system. Why this was interesting is because this galaxy seems to host a ring as well as a low surface brightness disk along with a bar, and it is also classified as a Seyfert-2 galaxy. So we wanted to know the origin of star formation in this galaxy, because the previous study tells us that as the bar frequency in galaxy increases, the specific star formation decreases, and in a way it curbs the ongoing star formation in the galaxy, and the same can be said for the effect of AGN on galaxies. These two processes tends to curb the ongoing star formation, whereas this galaxy was blue in color. So, and these massive blue galaxies are typically seen as the major merger remnants, but since this galaxy resides in an isolated environment, so the major merger is unlikely to explain the ongoing star formation. So first we did some structural analysis for this galaxy. We fitted 5 components in this galaxy using SIR6 exponential and truncated exponential function. This function was used to model the ring in the galaxies, and these two for bar and the disks. So, so this is our result. So this is CFHT observation of the galaxy. This is our model and the residue. So what the structural parameter tells me that this galaxy turns out to be disk dominated. Nearly 60 to 70% of the light reside in the disk, and it does not have a classical bulge, and also it has a very strong but a small bar inside it, and the absence of a prominent classical bulge negates the possibility of a major merger interaction in the past. So next we wanted to explore the nature of underlying AGN in this galaxy. So we did SED modeling for it, combining fluxes from FUV to mid-IR, and we were particularly interested in finding out the frac AGN parameter in this galaxy. Now frac AGN parameter is just the ratio of IR luminosity of the AGN versus the total galaxy. So in all the scenarios we got frac AGN for this galaxy less than 0.2, which signifies that the AGN is low powered in this galaxy, and perhaps this does not affect the ongoing star formation. Now with the integrated star formation that we get from SED modeling, we wanted to see where the star formation of this galaxy lies compared to a local sample and also a sample of void galaxies in a similar mass range. So these open circles are also void galaxies, and the background sample is just a random sample of local galaxies. So we find that the specific star formation of this galaxy is about half a disk higher than the main sequence, and also the next step was to find out where exactly is the star formation going on in this galaxy. So we made use of a color map. Now in this color map we can see that the bar inside the galaxy is really star forming, and this ring host star forming clumps. Even the FUV observation of this galaxy truncates beyond the 5 kiloparsec, and the integrated component wise color tells me that most of the star formation in this galaxy is going on inside the bar, and perhaps the ring and the disk is fairly red. On deep observation of this galaxy, I find that this a tidal tail feature and which perhaps confirms the possibility of minor merger interaction, and this minor merger interaction is inducing a bar formation in the galaxy, and the low luminosity AGN is unable to quench the ongoing star formation. Now the next part of my thesis was concentrated in finding out filament galaxies and studying their evolution. So we made use of this temple catalog. What it does, it uses Weiss's algorithm to find filament galaxies in observational data, and this diagram shows the sky map of my UVIT observation. These two circles are the field of view of my UVIT observation. The blue color markers are the galaxies that we detect in our observation, whereas the red ones were undetected. So we want, and these are all filament galaxies that I have highlighted. So I wanted to know where actually we are getting the detection in the filament. So I used this parameter called D filament. It is the distance of each galaxy from the filament spine, and what I found is that I detect no galaxies with UV emission within 0 to 0.4 megaparsec inside the filament, and the detection starts after 0.4 megaparsec, and these galaxies that were detected mainly belong to the blue cloud area in the color magnitude diagram. When compared to the galaxies that we detected in our earlier part, what we see is that the void galaxies had more higher FUV specific star formation than the filament galaxies. Now since we are detecting galaxies at the massive end in this in my observation, I compared their evolution with their specific star formation with cluster galaxies. So this x-axis indicates the distance of each galaxy from the filament spine, and for clusters shown with star markers, the distance from cluster center is indicated, and this is FUV specific star formation. The color bar shows the stellar mass of this galaxy. So I see a definitive trend in the specific star formation of filament versus cluster galaxies, which highlights the impact of large scale structures on galaxy evolution. I see that the FUV specific star formation for filament galaxies increases radially outwards, whereas no such effect is seen for cluster galaxies. Now here I compare the optical as well as FUV morphology of filament galaxies. So these blue contours are optical contours, and the outer one is at 1.5 sigma, and the red markers are the centroids for optical discs, and whereas the cross markers are the centroids for FUV disc. So what I want to highlight some of these galaxies show some extended FUV emission in them, and these galaxies are essentially situated in the outskirts of filament, are in the outskirts, and whereas galaxies like this are mostly concentrated in the center of the filament region. So the leaking of FUV emission out of the optical contour highlights towards maybe cold mode accretion in the filament environment. So this is the conclusion of my talk. The first two are like published in APJ, and the filament part is under review, and this is my publication. Thank you.
Yes. Anand?
Hello. I don't know how serious you were. You said that the bar was forming younger star. But most of the cases, what happens in the bar don't have young star but old star. The tip of the bar only have younger stars.
Sir, as you can see here, and sir, this is the color map for the bar, and also I have calculated component-wise colors. I have done structural modeling, and so I have all the magnitudes of each component, and from there, and also from the FUV emission that I have not shown. Actually, this is a outlier case that the bar here is like it has blue color and it's star forming.
Yes.
You had mentioned that the extent of the Buddhist void is from redshift of 0.04 to 0.06, and also that most of the galaxies you are working with, you only have photometric redshift.
For voids, yeah.
Yeah. So what is the accuracy with which you can get the photometric redshift from the data that you have? And what is the typical delta Z?
Okay. So the delta Z I do not remember, but based on what I can say right now is that we had taken the effect of delta Z in photo Z, and that's why we apply this probability, like we calculate the for each these are the probability density, and we shortlist these 4 galaxies. I don't remember the number of delta Z.
Other questions?
Massive galaxies are comparatively red in both the void as well as the cluster, while the smaller galaxies are bluer in the void. Now, if you look at BCD galaxies, for example, they show a red blanket under deep K-band observations. Is it true for your void galaxies also? Are there any K-band checks for this underlying red stars, set of red stars?
Ma'am, could you repeat? So you're saying
No,
that whether these galaxies have a red population?
No, you mentioned a comparison between the bigger more massive galaxies in the void and the more massive galaxies in the clusters. Both are red, more red galaxies for the more massive ones. For the less massive, you said in the void region, they are bluer. Now there is this observation regarding BCD galaxies that they are quite blue, but if you take deep K-band observations, you see an underlying red galaxy. So a similar thing is there for your lower mass galaxies in the void also.
So this is one of the possibilities that we have discussed in our discussion, but I also looked at their IR observation of these galaxies, and there were no detection. That's why when I was doing this the photometric redshift calculation, I wanted to take in the fluxes from IR observations as well, but there were no detection for these galaxies.
Thank you.
Right. There are no other questions. And thank you, Divya. The next speaker is Soumya Ranjan Das. He's going to talk about modeling the evolution of magnetic fields and modeling the evolution of solar coronal magnetic fields and its impact on the heliosphere.
So lights will be on. Thank you. So good morning, everyone. So I'd like to start my presentation with a very nice picture of a sunset, which is actually, it's the sunset time where I am a postdoc, as I'm working as a postdoc at University of Hawaii, and this is a sunset picture from the Haleakala summit, where we have the Dick East telescope for observing the sun. Sun is our host star, and in my thesis, I am trying to understand the evolution of solar coronal magnetic fields through modeling and its heliospheric consequences. So when we look at the sun through a telescope, we see something like this, and these are the dark locations which are the sunspots. But the sunspots are highly magnetically intense. And if we take an image, a high resolution image from a space-based telescope, then we see more structures in those dark locations. Now, since all the activities that are happening on the sun are mediated by magnetic fields, then we need to understand how the magnetic field distribution on the sun surface looks like. So we have that from those space-based instruments. One of them is HMI, and we see these positive and negative polarities. Positive are white and negative is black, and this is a typical magnetogram of the sun surface. Now, we understand that, okay, this is from direct observations, and these magnetic fields, they originate through a magnetohydrodynamic dynamo process in the sun's interior. They manifest on the surface, they extend into the solar atmosphere, which is known as corona, and also various magnetic activities we observe in the form of solar wind distribution, open flux solar wind acceleration, open flux distribution, they are caused by the magnetic activity on the solar surface. But we do not have direct observations of those magnetic fields in the corona. So what we do is we use whatever we have, whatever we observe on the surface, and use theoretical models to extrapolate the magnetic fields in the corona. Now this is important to understand that if we have observations of the coronal magnetic fields, then we will have more confidence on our calculations. But we also we have these surface magnetic fields to constrain these theoretical models, and I will explain through some of my thesis work that how we are doing that. So as I said, magnetic field that gets generated in the sun's interior is seen on the surface, and its impact is felt in the total inner heliosphere, and it reaches us also through different disruptive dynamics, solar wind acceleration, and global open flux distribution in the inner heliosphere. Now, in all these events, they rely on the large scale distribution of the magnetic fields. So our research goal is to understand the large scale structuring of solar coronal magnetic field. Those are driven by the internal dynamo process and surface flux transport processes. And we need to understand also how these large scale structures, large scale magnetic fields and their evolution, they impact the heliospheric changes. So the different kind of numerical models that I have used for my thesis are the solar dynamo model. I have used a 2.5D kinematic dynamo model in Surya. I have also used a surface flux transport model that was developed at SESI. I also have used a potential field source surface extrapolation model for my analysis. So let's go to the first project, where our first goal was to understand the large scale structuring of the solar coronal magnetic fields. Now coronal magnetic fields are not usually seen routinely, but what we can do is, during a total solar eclipse, when the disk is completely occulted by the moon, we can see the solar corona, the large scale solar corona we can see. Now if we use the models, theoretical models that we have with us to predict the magnetic field structure of the solar corona for a total solar eclipse, then we can compare them and then see how well we are doing in terms of theoretical modeling for the large scale structures of the coronal magnetic fields. So for doing that, what we did is we ran a surface flux transport simulation until 53 days prior to the date of the eclipse, and then reconstructed these magnetic fields in the corona. So this is our prediction for the total solar eclipse of 2019 July 2nd. And after the event happened, we took the direct observations from HMI of the surface magnetic fields, and again extrapolated the large scale magnetic fields for the corona, and we compared these to our prediction and the observations. And we see a reasonable match. We see this large scale helmet streamers that are there in both observation and our prediction, but however the tilt is not exactly accurate, but still there are some constraints to what we can model and how the observations are. And for this particular event also, what we did is we also computed the polarization characteristics, because what we are observing or what we will observe through our VLC instrument is the polarization vectors, IQUB basically. So we did a forward calculation of these polarization vectors, and we showed that, so this is the total brightness from our calculations using the PFSS model and the surface flux transport model. So this is the degree of linear polarization, this is the degree of circular polarization. And all these calculations, for doing that, all these calculations, we use the forward tool set that's publicly available. Now, as I was saying that the tilt angle that we predicted was not matching exactly with the observations. Why we cannot directly match those observations? That though the reason can be due to the uncertainty in the observation or modeling in the polar field locations. So now, if we consider this to be a standard case, then when we reduce the polar field artificially by a factor of half, then what we say is the tilt angle of the streamers are more towards the poles, which says that the net poleward pressure on these streamer tilts is very less if we have less polar field amplitude. If we have more, so this set of 2 points, they show that if we double the polar magnetic field value, then the streamers are more squeezed towards the equatorial locations. And this is the kind of experiment that we can do using theoretical models. And the large scale structure we can reconstruct and compare with actual observations, and that is helpful to understand, that helps us understand how the net evolution of the magnetic fields will impact the global heliosphere. Now that we model these global structures, magnetic field structures, let's understand how that impacts our heliosphere. In our heliosphere, what we observe, okay, let's consider on Earth what we directly get is cosmic ray fluxes. We have direct observations of cosmic ray fluxes. We can calculate the cosmic ray modulation potential, or how sun's magnetic field activity impacts the cosmic ray that we receive on Earth. So to model these kind of events, what we used is, we used a set of dynamo simulations, PFSS extrapolations, and some analytical calculations. So we ran the dynamo model for 6,000 years with stochastic variation in the polar del source, which creates these extended periods of global minimum. These are known as grand minimum, and there are also locations where there are activities like grand maximum, and there are locations of regular activity phases. So for these three kind of distinct activity phases, we have studied how the changes in the output into the heliosphere, which can be quantified through the open solar flux calculations and the cosmic ray modulation potential that we have studied for these three different activity epochs. So this is one example. So where I am showing that this is for a grand maximum phase, where the number of sunspots is unusually high as compared to the other regular phases. Now what you see here is the black lines show the closed field lines, and these different colored lines are open field lines. One is for positive and this is for negative. So this starts from negative, this starts from positive polarity. Okay, so for a grand maximum phase, most of the closed field lines are found close to the equatorial locations. But for a grand minimum phase, when there are no sunspots available on the surface, then these are the small scale polarities that are scattered around the surface. Now, due to those small scale polarities, we see some closed loops which are very low lying in height, and there are very less open field lines found during a grand minimum phase, as opposed to a regular activity when we see a mixture of open and closed field lines throughout the surface. And what you can see here in this plot is, you see that the magnetic field amplitude during these three different phases of solar activity is actually different, and you expect for a grand maximum phase to have the highest value of magnetic field, or the magnetic flux is the radial component of the magnetic field, and eventually it will decay, it will be less when we have a regular activity, and for a grand minimum activity it will be the least. Now, what are the changes that we can do for this modeling? Because all the theoretical models have certain assumptions that we can change, and that will impact the results also. So, one of such free parameter in the potential field source of extrapolation is the height of the source surface, which is conventionally taken to be 2.5 solar radius. But if we change the source surface to a lower height, then what we are seeing is the open flux that we get near the source surface is increased. So, now remember, this is one of the free parameters of our theoretical model. As we do not have direct observations of these coronal magnetic fields or even open flux, during those grand minimum kind of phases, we cannot directly constrain our theoretical models to change cycle to cycle or activity to activity phase for modeling these global structures. Now, but what we can do is we have observations of open flux. So, these are calculations from the proxies that we get from the cosmogenic isotope studies. We can calculate these open flux for almost over 1,000 years. There are also decadal averages of observations which spans more than 10,000 years. So, from this observations, direct observations or proxies of those observations, we identify two locations. One is a grand minimum phase and one is a regular activity phase. You expect during a regular activity phase, for a regular activity phase, the cycle period, the solar magnetic activity cycle period to be of 11 years. Now, for a solar minimum phase, this is not 11 years. So, what we are seeing is there is a shift. So, the cycle or the polar field is reversing much faster as compared to our regular activity phase. Now, remember, that was from observations, and this is from our model calculations, where from these modeled open solar fluxes, we see that we can recover the 11-year periodicity, and for the open solar flux, we for a grand minimum phase, there is a decrease in the period 11 years, and the similar trend is found in the cosmic ray modulation potential as well. So, now I will quickly describe this part of our project, where we are trying to understand the impact of this large scale magnetic field on the magnetic flux that are associated with a CME magnetic cloud, how they erode due to these large scale magnetic fields when they propagate through the heliosphere. So, now what we find here is we identified a set of events, almost 73 events, where the magnetic clouds can be clearly identified, the front and leading edge of the magnetic clouds, and we see that their geoeffectiveness decreases when they interact with the open solar flux that is already, the ambient open solar flux that is already there in the heliosphere. And we can see that there is a clear solar cycle correlation for this particular kind of study. And so, what we see is if the open flux is more, then the erosion will be higher for magnetic cloud. This study also has been published as a GRL paper. So, now I will just summarize what I said until this point. So, modeling the large scale magnetic fields in the corona, which shapes our heliospheric environment, but it is very hard to directly observe. That was our prime, that is a prime importance, and it is really challenging. So, what we have demonstrated is we demonstrated the modeling of large scale corona with predictive capability in the time scale of the order of solar rotations when there is a minimal solar activity cycle going on, and we also calculated the polarization vectors. The polar field observations are also important, and consequently what we saw is we established a causal connection between the solar activity in the interior and the heliospheric dynamics in the interplanetary space. And we also showed that the large scale fields, how they interact with the magnetic clouds and reduce the geoeffectiveness, and that has a solar cycle dependence as well. So, I will just leave with the slide here. So, here you see the Dick's telescope, and again this is the Helicala summit. Thank you.
Questions?
So nice work, Sobranjan. So, hello. Yeah, so at curious that did you also calculate magnetic filling factor for this open and closed magnetic flux and see how well it matches with your simulation?
Open and closed magnetic fields?
Yeah. So
for the grand minimum cases, right?
Yes, grand minimum or even the maximum, because you see the trend, you have a long time grand minima. So in that time, did you find any way to compare the filling factor?
Right. So we tried to do that, but we could not find a clear correlation between these three different distinct phases of the solar cycle. But we tried doing that. We tried different mechanism, like taking the radial component at the solar source surface as a proxy for different three phases, but there is no clear relation, or there is no clear trend for these kind of theoretical calculations specifically. When we do not have direct observations, it's very hard to constrain the theoretical models.
Any other questions? All right. I don't see any other hands up. So thank you, Somaranjan.
Thank you.
So we'll continue in the theme of the sun with Vishal Upendran, who's going to talk about heating and dynamics of the solar atmosphere.
Hello? Hello, can you hear me? Yeah, okay, I can hear myself. Thank you, and good morning, everyone. I am Vishal Upendran. I am a postdoc at Lockheed Martin Solar and Astrophysics Laboratory right now. I did my PhD at IU Pune with Professor Durgesh Tripathi on the heating and dynamics of the solar atmosphere. The solar atmosphere starts from the photosphere at 5,005 degree Kelvin and extends all the way up to the corona at more than 1,000,000 degree Kelvin. The solar atmosphere, as you can see from these plots, is stratified and consists of various layers like the chromosphere and transition region. The atmosphere is not just stratified in temperature and density, it's also coupled together by the dynamics of the magnetic field. The atmosphere further extends out much further into the heliosphere and becomes free streaming into what is called the solar wind. The solar wind is basically a stream of particles, and the properties of these stream of particles can be measured by putting a probe, let's say, at L1. And we all know what has gone to L1 right now. The solar wind, as has been measured historically in situ and also through remote sensing observations, is known to have structures, is known to have two primary structures. One is called a fast wind, which is very fast, and the other is called slow wind, which is quite slow. These structures in solar wind are known to have associations with structures in the corona. The solar wind itself is known to have a strong association with dark structures on the corona called coronal holes, while the slow wind is also known to have associations with these bright structures called the active regions. These intensity enhancements and deficits are known to occur on top of a background called the quiet sun. With this in mind, we asked the following questions in our thesis. What are the typical mechanisms that heat up the corona? As you have seen, the temperature of solar atmosphere rises from the surface, from the photosphere to the corona. This is an anomalous increase in temperature. What causes this rise in temperature? And what are the typical dynamics? What is the difference in dynamics between regions that give rise to solar wind and that do not give rise to solar wind? And finally, what are the typical sources of solar wind, and are we able to forecast solar wind properties given changing conditions on the sun? We take up each of these questions one by one in this thesis. So typically the sun is known to exist in two states. In one state where it's very extroverted and giving a lot of dynamics, and there's a lot of flares and transient activity going on large scales. But the sun has a more calm and diffuse state where you don't have these large transient activities keep going on, but rather you have very small scale activity that's always occurring. This state, where you don't have a lot of large scale activity going on, is called the quiet state, and most of it is called quiet sun. This quiet sun is also at 1,000,000 degree Kelvin. So if we really need to understand why the solar atmosphere is so hot, we need to understand why the quiet sun is so hot. And that's what drives the first problem. What are the properties of the heating mechanisms of the quiet sun regions? Now, we have a strong inductive bias in this case through the observations of impulsive events. When I say impulsive events, these are transient events that occur at various length scales, time scales, and energy scales across the solar atmosphere. And these are known to follow a power law distribution, as shown here. A power law distribution of such event sizes and energies may actually arise from scale-free processes. So it is not an unreasonable expectation to say that this quiet solar corona is heated up by a very small scale impulsive or transient events. Usually people would go and actually measure the size and properties of these individual events. What I have there is a typical light curve from a pixel in a quiet sun region. And if I were to ask you exactly how many events are there, it's rather difficult to say this is actually an individual event. It could actually be a set of unresolved events which your instrumentation can't resolve. That is giving rise to what intensities we see. To counter or to understand or to infer the properties of events given these kind of light curves, we developed a machine learning algorithm which is trained on simulations. These simulations consider a train or a chain of impulsive events, unresolved impulsive events, that give rise to light curves in quiet sun regions. The machine is trained to recognize, is trained on the light curves and trained to recognize the properties of these light curves. And it is then deployed on observed data. We have approximately used 1 million light curves from quiet sun regions in different pass bands. In AIA, in EUV, in extreme ultraviolet in one case, and in using the Chandrayaan-2 XSM data in the other case. So while performing this inversion and this analysis, we plot here the observations in orange and the simulation, the best fit simulation if you want to think of it, in black. These two show an excellent match, especially if you consider the intensity distribution match and the wavelet power spectrum match, where you see similar scales being deemed important in both the simulation and observation. The events that give rise to this light curve are typically have energies less than 10 to the 23 ergs, which are known to fall in the nanoflare and picoflare energy regime. We also look at how the properties of these different events vary across different temperature bands. And we find that there is a gradation of properties as you go from cool to hot pass bands. First, we find that the event frequency in time actually is anti-correlated or inversely proportional to the typical amplitude of these events, which points to an energy reservoir which can be depleted by large events occurring very intermittently or small events occurring very frequently. The time scales are reduced with temperature, pointing to an increasing impulsiveness of these individual events. And a change in this power law slope alpha from more than 2 to less than 2 possibly hints at a change in the energizing mechanism of these different events. With this in mind, we go and ask what are the differences between coronal holes, which are very well known as the dark structures and sources of solar wind, and these quiet regions. So this image you have here is in the corona, where you actually have the coronal hole. Now you can see why it's called a hole. It's like literally a hole in the corona. As you probe these regions lower and lower into the atmosphere, and by lower, I mean at lower and lower temperatures, we start to see that the difference actually starts vanishing. And somewhere low in the atmosphere, you really don't see any visual discrepancy between these coronal holes and quiet sun region. So two regions which are very similar, lower in the atmosphere, are extremely differentiated, very high in the atmosphere. One has excess local heating, and the other gives rise to solar wind. What's going on between these highs? This is what we seek to understand in this set of projects. We use various spectral lines which form at different temperatures, as marked here, and these probe from the lower chromosphere to the transition region in the solar atmosphere. We use iris data for doing this work, and this has been published in a set of 3 papers, of which 2 are a part of my thesis. We look at the intensities, velocities, line widths, the kurtosis and skewness of these spectral lines, but what we do differently is we look at it as a function of the underlying photospheric magnetic field. That differentiates the coronal holes and quiet sun region. We find intensity differences already in the chromosphere. You don't see them visually because the distributions are by and large similar. But if you bin them in magnetic field, you see these differences pop out because these are very minute statistical differences. We also find that on an average, the velocities are similar between the 2 regions. But if you take the blue shifted and red shifted pixels separately, you find persistent excess outflows in coronal holes already in the chromosphere. The solar wind is already starting in the chromosphere itself. And interestingly, we find excess plasma downflows, that the plasma is preferentially going down towards the photosphere in the chromosphere. But in the transition region, that's not what is happening. It's happening in the quiet sun regions. So there is a dichotomy, as we see, between the chromosphere and the transition region, between coronal holes and quiet sun. To understand this dichotomy, we also look at cross-correlation between the flows in different regimes. And we find that we find signatures of persistent downflows, persistent upflows, and bidirectional flows in this whole system. So plasma is preferentially going out all the way from the chromosphere to the transition region, falling down all the way, and there are bidirectional flows. What could possibly be explaining these kinds of flows? This is the classic observation from many years ago, which discovered that solar wind in coronal hole actually starts in funnel-like structures. And as you can see, you have the funnel-like structures, and you have a lot of small loops everywhere in the background in the coronal hole. So what we propose in this paper, along with these observations, in a lot of observations and simulations, is that coronal heating and solar wind emergence is an emergent phenomena occurring due to the same process. We have impulsive events which are manifested through reconnection events as closed-loop reconnection in quiet sun and interchange reconnection in coronal hole. And reconnection events naturally give rise to bidirectional flows. And these open flux systems naturally accelerate upflows much strongly. Whereas in the closed loop system, the plasma is not able to escape, and it just stays trapped in the loop structure, giving rise to local heating and filling of plasma in these loop structures. So you see these excess intensities in these quiet sun systems. We didn't just stop there. We wanted to eliminate our observations, as the late Paddy sir would say, with simulations. And so what we did was we performed flux emergence simulations and different background magnetic field topologies in 2.5D MHD. And we synthesize spectral observables. We find signatures of a hot jet and a cool jet riding on top of each other, and the orientation of this jet depends on the background magnetic field, which is horizontal in quiet sun and most vertical in coronal hole. So because of this difference in orientation, we see signatures in line-of-sight Doppler velocities. We also find that these cool and hot jets are actually co-spatial if you look at it from the top, but these are two different distinct creatures. It is not, as we had initially assumed, that the same plasma parcel which is cold is all the way getting hot. There are two jets that are coming on top of each other, and that's what these simulations reveal to us. With this information, we finally go and ask, can you perform solar wind forecasting? So this problem is stated as this. We want to translate a sequence of input solar images into a sequence of in-situ measurements. We perform this translation from one time series to another time series using a deep learning model. This deep learning model is able to forecast the solar wind speed 4 days before the solar wind actually comes and hits the earth. And once the forecasting is done, we go and ask the model for a fast wind forecast. Remember, we had the fast and slow wind early on. For a fast wind forecast, what regions on the sun are important? And for a slow wind forecast, what regions on the sun are important? That's the question we ask to the deep learning model. What we find is summarized here. This set of images is for a fast wind forecast, where you have the input images in the extreme ultraviolet on top. And these are importance maps. The redder the color is, the more important that region is. And we find that for a fast wind forecast, these coronal holes are deemed very, very important 4 days before the solar wind reaches the earth. For a slow wind forecast, we find that the active regions are rather important 6 days before the solar wind actually reaches the earth, whereas the coronal holes show some enhanced importance 4 days before this forecast. Why am I stressing on these 4 days and 6 days? These are the numbers that we actually obtain from observations if you cross-correlate properties of coronal holes and active regions with properties in solar wind. So this model is telling us a physical relation without even us giving it the physical relation as any model or any set of equations. So we go and look at the full data set, which is 8 years at 1 day cadence, and these are 512 cross 512 images, to statistically understand what is happening. We find that if you perform a statistical analysis across the whole data set, we are able to recover this relation where the coronal holes are strongly associated with these fast wind structures. The active regions are strongly associated with slow wind structures. The association between coronal hole and fast wind is very strong, and it is seen at exactly 4 days before the solar wind hits the earth. The time scale here for the active region, however, is different. It's much closer to the day of forecast. And this occurs because active regions are small long-lived structures that are seen over multiple time steps. And remember, this work was done in 2020, or rather, it was started much earlier. So machine learning is a field that grows exponentially. And during that time, this was the most advanced algorithm we were using. And this algorithm itself had this bias that if it sees a structure much early in the time series or much later in the time series, it's just going to ignore the earlier instance of that particular feature. So with this method, with this application of RATCAM, we are able to recover both biases in the model and also extract the physics out from this association. So the key takeaways from these theses are impulsive heating is very viable in quiescent regions. And this impulsive heating may be manifested through interchange reconnection in kernel holes and closed loop reconnection in quiescent. And they provide signatures as intensities, velocities, line width, if you take optically thick emission, also in skewness and kurtosis of different spectral lines. Lower in the atmosphere, you have these differences, but you see these differences only if you account for the underlying photospheric magnetic flux density. You also find that morphological structures in the corona show the strong association with structures in solar wind, and these can be very significantly recovered by the application of deep learning and interpretable AI. And I would go so far to say that if you pose your problem properly, which is very, very important, and if you know what your model is, if you just don't take an off-the-shelf model, if you know what your model is doing, and if you have good enough data, you should be able to recover physical associations between these different variables in any physics domain. These are the set of papers that went into my thesis. So the pre-final paper on the simulation is under review now, and that's because I had to finish my thesis 6 months before I was even stipulated to finish, and I had to leave for my postdoc. So I'll stop there and I'll take questions. Thank you.
It's open for discussion.
Do you see any correlation with actual data from solar orbiter or something for your model now?
Yes, so good question. So we actually have I and Durgesh, we got a grant from NVIDIA to do this work along with using Solar Orbiter and Parker Solar Pro. And that is actually being done at IUCAA right now. And the thing is, since you have different vantage points, that information of different vantage points has to be fed in a mathematically consistent manner into whatever model we deploy. So that is something we have done by using a spherical grid, but we don't really have any results yet. So not in this work, but in the next work, yeah. Thank you.
So, hello. So, I am just curious.
Vagesh, we can't hear you.
Hello.
Yeah.
Yeah, so I'm just curious that when you do this deep learning things, so you are basically trying to predict the speed of the slow and fast solar wind, but I'm just like thinking why not other thermodynamic properties and associate with some in situ data to see how well the model works, as we know kinematics and thermodynamics may be connected, right?
Yes, and I didn't catch you, but I have a poster down where you were doing something similar with density, temperature, magnetic field properties, because that's more important. The thing is, we wanted to start off, so this is the first paper which actually uses deep learning to do this kind of forecasting in solar physics. Nobody has done this interpretable machine learning in solar physics at all before this. So you wanted to first showcase it works on a simple problem, which is solar wind speed, and then generalize it to other problems. So, thank you.
So this aspect of solar wind prediction by using AI, so far have you tested is only for the situations when there was no flares or CMEs, or have you also done it in the situations, or do you have better results when these eruptive phenomena are absent or when they are present, or can you comment on that?
Yes, so this data set we use is at 1 day cadence. So 1 day cadence is not actually enough for capturing any CME or flare dynamics. So we removed all the places where we have ICMEs. It is, I think, far more difficult if we are to forecast CMEs with deep learning, but there's an effort going on. It's just difficult because we need stereo data, for example. So we need to incorporate multiple vantage points and multiple data sets to understand and there is a lot of in situ process that happens in CMEs, and that is something that we may either need to model or we'll need to have some other data set to incorporate. So in this work and any other work I'm doing, we don't have any CMEs right now, but that's a different effort. Yes, thank you.
Anyone else?
Yeah, the machine learning plots that you showed are very intriguing. So I am curious how your machine learning is able to correlate morphological features on the sun with kinematical features of the solar wind. How did you train the network, and how does the model go about recognizing which feature is responsible for what kinematic aspect?
Very nice. So what machine learning does, or what rather we do, is we try to break down whatever we see into certain structures. Let's say we do high pass filter. I mean, I'm talking not as a person, but as a system which is taking some input and doing some processing. The machine basically in the first couple of layers tries to break down the input into various, into high pass filtered structures, low pass filter structures, and various structures. And then it does nonlinear transformations and tries to find the most correct transformation, which is able to transform this variable into solar wind variable. So when I'm doing the estimation of what the source regions are, what I'm asking is which pixels in the input image are the most important. And what I mean by most important is if I change the input pixel, my target, let's say it's a fast wind, my target fast wind prediction changes drastically. So which means those pixels are important. So that is how the whole interpretation theory is founded. And that's how the modal machine, if you want to really think of it, it's just a gradient descent and Learnberg Marquardt or whatever you want to just optimize any set of parameters. It's glorified curve fitting. But it's much more subtle than that. It's also decomposing it into various basis functions. And that basis function is what we estimate through training by using different data.
Thank you. Shall we have to move on? Yeah. Next speaker is Akash Garg, final speaker of the session. He's going to talk about probing energy-dependent timing behavior of X-ray binaries.
Hi everyone, I'm Akash Garg. Before I start, I want to thank the esteemed panel of ASI for this chance to present my thesis work again. I did my PhD from Jamia Millia Islamia, Delhi, India, under the supervision of Dr. Samashri Sen from Jamia Millia Islamia and Professor Anjeev Mishra from IUCAA. I defended my thesis on 23rd Jan 2023. I'm currently working as a postdoctoral fellow in IUCAA, Pune. The title of my thesis is Probing Energy-Dependent Timing Behavior of the X-ray binaries. This is the brief outline of the talk. I'll introduce the X-ray binaries and accretion disk. I'll talk about the motivation of the thesis and about the methodology that we took for this thesis work. Then I'll summarize and conclude, and then lastly, I'll talk about the application of our research findings. So I thought it is best to start with these images of different black hole systems taken using Chandra X-ray Observatory. What you are seeing, these tiny and shiny dots in the different parts of the electromagnetic spectrum, but they are not alone. They have a binary partner, and they are also not stable. Their flux, their luminosity is changing with respect to time. Before I explain what these systems are, let me tell you a bit about the stellar evolution. We all know that the star, as it enters the red giant phase, if it is a smaller star, it will take the upper trajectory, and will, as it exhausts its supply of gas, it will undergo the planetary nebula phase and will end up in a white dwarf. But if it is a bigger star, larger star, then the supergiant will exhaust its supply of gas, will take the lower trajectory, and will undergo the supernova explosion and will either end up into a black hole or a neutron star. So basically, there are three end products of the stellar evolution: a white dwarf, a neutron star, and a black hole. Now, these compact objects can come into a binary relation with a normal star, a sun-like star, and can create something known as X-ray binary systems. Both the stars, they are orbiting around their center of mass, and this is basically a restricted three-body problem, also known as Roche problem, where besides these two stars, there is also the exchange of the matter between the two stars. Both these massive bodies are supposed to trace Kepler orbits about each other in this X-ray binary system. Now, this matter transfer can occur either through a Roche lobe overflow or a stellar wind accretion. In stellar wind accretion, the companion star may eject matter in the form of stellar winds, which will then be captured by the strong gravity of the compact object. But in the Roche lobe overflow, it so happens that the secondary star, it swells up and fills its Roche lobe, and then if there are some small pressure perturbation, it can push the matter down the Lagrangian point L1 and will start the matter transfer between the two objects. Now, this transferring material, it has very high angular momentum, which it has to lose before it can reach the compact object, and this leads to the formation of an accretion disk. The gaseous matter, it possesses gravitational potential energy, which is what is emitted out in the form of X-rays, and which is what we receive using different space-based satellites. Now, in this thesis work, I mostly focused on the black hole X-ray binary systems, and for most of these systems, it has been found that their light curves, they are very chaotic, or their count rate is changing very rapidly with respect to time, as you can see in this left panel here. So it is difficult to identify any characteristic frequency. So what we do is this Fourier trick, we Fourier decompose the light curve and create something known as power density spectrum. Now you can see these narrow features here, and these narrow features in literature are known as quasi-periodic oscillations. They possess multiple properties, but two of them are very interesting and they are energy dependent. The first one is the fractional root mean square RMS. This is basically the total power of the QPO. This tells us about the strength of the QPO. The other one is the time delay. So it is possible that there are two light curves in different energy bands, and if you detect them simultaneously, they can have a time delay. You can estimate that using the cross correlation between the two light curves, and this is also found to be energy dependent. So we mostly use these two properties in my thesis work. Now, there are different possible ways to explain the origin of QPOs. One way is to identify the QPO frequency with some kind of theoretical frequency, like done in all these work, lens-saving precession frequency and shock oscillation model, and many more. The other way, possible way, is to identify the radiative process that can give rise to the QPO frequency. This is basically based on the correlation between the spectral state of the source and the QPO characteristics. So we took this second way in our thesis work. Before I go on to explain the generic scheme that we developed, let me tell you a bit about the energy spectrum. So it is known that for most black hole binaries, their energy spectrum is most of the time dominated by these two radiative components. The soft component, represented by these red points, it dominates in the low energy band. It has black body nature, and it is believed to be emitted by some optically thick and geometrically thin disk. The hard component, which is dominating in the higher energy band, it is power law in nature, and it is believed to be emitted by some optically thin and geometrically thick hot region. Now let me come to the methodology. So we know that both these components, there's a NASA software XSpec, where both these components can be modeled using the inbuilt models like disk BB and THCOM. The disk BB has two parameters, inner disk temperature and normalization of that model. The THCOM, it has three parameters like electron temperature, spectral index, and scattering fraction. But they are spectral parameters, and we need to translate them into physical parameters to obtain better physical information about the accretion flow. So as a first step of the scheme, we translated them using these relations into the physical parameter. And this is the table for that. So we translated inner disk temperature to accretion rate, normalization to inner disk radii, photon index to optical depth, and electron temperature to heating rate, and we kept the scattering fraction as it is. Just to give you the idea how these parameters are related to geometry, so these two arrows here, the blue arrows, they represent the accretion rate in inner disk radii related to the accretion disk, the truncated accretion disk. The other three parameters, they are related to the coronal geometry represented by these three orange arrows here. Moving on. Now that we have the information about the spectrum and their parameters, physical parameters, as a second step, we varied the spectrum with respect to all those physical parameters to calculate the first order variation in the spectrum. And with that first order variation, we could calculate the RMS and phase lag. So if you remember, these are the same two energy dependent quantities which has been observed for the QPOs. So now we are predicting them for a model. Now we want to compare them with the observations. So these are the predictions for the variations in accretion rate parameter and coronal heating rate parameter with some delay between them. We wanted to test them, how good these predictions are. For that, we took the AstroSat observation. It's an Indian multi-wavelength observatory. It has 5 scientific instruments: LAX-PC, SXT, SYZT-TI, UVIT, and SSM. And mostly in this thesis work, I took the data from the LAX-PC and SXT. LAX-PC covers 3 to 80 keV energy band, and SXT covers 0.3 to 8 keV energy band. And we took the data from these 2 satellites. Now, in the first work, we tested the model for this popular black hole system, GRS 1915 plus 100 plus 105. And as a first step, we fitted the spectrum using the disk components and the high energy component. We figured out the parameters here. And multiple works have shown that there's a sharp QPO at 3.5 hertz. So we fitted our model for the RMS and lag observed at the 3.5 hertz QPO. So all these Shan points, they correspond to the observations, and we fitted with our model. So in our model 1, we don't overcomplicate the models by taking variation in all the parameters. We consider variation in accretion rate and coronal heating rate with some delay between them and checked with the observation. We find that it's not a good fit. So we moved to model 2, consider variations in inner disk radii as well with some delays, but we again find that it's not a good fit to the observation. So we moved to model 3 and considered variation in one more parameter, which is the coronal optical depth, and we find that it can fit the data in better than the other 2 models. So we found this interpretation that correlated variation in all these parameters with some delays between them can explain the observation, but this was done for small set of observation. So we wanted to test it for more observations. So in a different work, we considered the black hole, another black hole system, MAXI J1535571. When it went into outburst, AstroSat observed it extensively for about 5 days. And there were about 63 orbits of observation. And for each of the orbit, people have seen that there are sharp QPOs. For reference, I have put here a typical power density spectrum, and you can see the sharp QPOs here around 2 hertz. So as a first step, again, I fitted the spectrum with the basic disk components and high energy components, and along with some absorption components. Before we fitted the RMS and lag, we thought to check, because there are multiple orbits, we thought to check the evolution of spectral parameters. We found all this evolution and an interesting correlation between QPO frequency and the scattering fraction. Then we fitted our model for the energy-dependent RMS and time lag. We started with a simpler model with just 2 variations, but we couldn't fit the data. So we moved to this other model with correlated variations in coronal heating rate, accretion rate, and inner disk radii. We find that it can fit the data. But the advantage here that we had is that we have large number of observations, so we can do it for all the orbits and see if there is any time evolution. All these plots correspond to the evolution of all the parameters, fitting parameters. Interestingly, we found this correlation between inner disk radii and accretion rate with some exponent 0.7 from this work. Another thing that we found in this work, that the observed time lag between these 2 energy bands, they switch their signs at around 2.2 hertz. It has only been observed for this another black hole system, GRS 1915, not for any other black hole by all these work. So this was interesting that we are seeing such a shift at this frequency, but in a very different spectral state of this source. So we thought to check, let's say, what our model says about this. So we fitted our model, the energy-dependent RMS and time lag correspond to all those frequencies. We find that for frequencies lesser than 2.2 hertz, our model says that the QPO originates somewhere in the disk. But for the frequencies greater than 2.2 hertz, we found that our model says that it could be the dynamic origin is in the corona. So we thought, and we stated in the discussion of our paper, that it could be that it's a resonance effect arising. The QPO could be the resonance effect arising out of both these origin. And this is what we are exploring in a different paper. We call it a feedback model between the corona and the disk, which is causing this QPO. But these are the results that came out of this paper. Now I'll summarize and conclude. So we worked on this generic scheme to estimate which variations of spectral parameter can explain the observed RMS and time lag. When we applied it to a black hole system GRS 1915-105, we find that the variation in accretion rate and inner disk radii, along with variations in coronal optical depth, heating rate, it can explain the observations. And we found that the primary driver of the phenomenon is the coronal heating rate here. For Maxi J1535, we found that correlated variations in accretion rate, inner disk radii, and coronal heating rate, it can explain the observations. We don't need another parameter here. But the dynamic origin of QPO is different for positive and negative lab. So these are the results from this work. Now let me come to the application of our research findings. Now different students, they are applying this model in different works, like for different black hole systems and neutron star systems. Like Hussain et al., they have done it for QPOs, sharp QPOs in H1743, 322. Hitesh et al., they are doing it for the broad features. So this model is not just applicable for the quasi-periodic oscillation, it is also applicable for the broad continuum that we see in the power density spectrum. So they are doing it for this object when it went into outburst in 2021. Twanga et al., they are doing it again for the broad features in Cygnus X1 in a different black hole system. And now they are doing it using about 4 to 5 years of data of AstroSat. Arvind et al., they are doing it for the QPOs in Maxi J1803298 for the full outburst. So this black hole X-ray binary, it undergoes its full outburst. So we wanted to check how our model works if we take every spectral state during the full outburst. So they are exploring this part for the model. Marius Bosco et al., they are doing it for the QPOs in both these black hole systems. All these people, they have the poster here. Ruchika et al., they have done it for more observations of QPO in GRS 1915, but in different spectral states. And then Shri et al., they have done it for the broad features in our neutron star systems. So they have checked that this model is applicable for the broad features and the kilohertz QPOs as done by the Suchishmito et al. In neutron star systems. So this explains basically the wide applicability of the research findings. And not just with the AstroSat data, some of these works, they are doing it using the nicer data as well. The thesis work is based on the following publication. With this, I end my talk. Thank you.
Anna.
So my knowledge of accretion disk is very limited, but people working in the field talk of a thin disk versus thick disk, and I suppose the physics of a thick disk is much more complicated than the thin disk. So in the kinds of cases which you are considering, what sort of case is applicable, and is model 1, 2, 3 which you discussed, have they have any relation with thick disk versus thin disk?
Yes. So thank you, sir. So for this work, we have considered that there is a thin disk which is getting truncated. There is a thick disk which is getting truncated at some radii, and then after that, near the black hole, there's a coronal region, which is hot region, which is supposed to be that it was some kind of thin disk, but sorry, I'm got confused. So let me show you the picture. Yes, so as you can see here, there's a truncated disk here, and this truncated disk is geometrically thin but optically thick. And then in the near regions around the black hole, we say that there is a optically thin region, but it's geometrically thick. So disk, we assume that it's geometrically thin, but in the inner region, we say that maybe the disk evaporated and then became some coronal region here. So this is the kind of picture that we are taking in this model.
Okay. Thank you for the nice talk. Okay, so I have a question. So when you told about the QPO frequency being higher than 2.2 hertz, so it would be coming from the corona. So when you are fitting the spectrum, like I didn't see a dedicated reflection model for the spectral fitting, like Rexil or some reflex. So is there a specific reason why did you consider reflection?
So thank you for the question. We start with a simpler model. We consider disk components and high energy component like THCOM, but we can take that reflection component and consider the variation in its parameters as well. But it will overcomplicate the model. So we try to fit with the simpler models. But yes, we have this plan to make this scheme more general so that we can take any expect component in the scheme. So like we do it for the spectral fitting, people can take any expect component. We want to do the same. People can take any expect component and then fit the temporal features as well.
Just one more thing. So did you classify QPUs also, they all are low frequency. So did you classify type A, B, C?
Sorry, classify?
So did you classify them as type A, type B, or type C QPUs?
There is already a classification.
Yeah. So you're only focusing on one. Yeah.
Yes. So that's why I said some of the students, they are trying it for the full outburst, meaning they are trying it for the type A, type B, and type C QPUs. So they are applying.
Thank you.
See, here's a
Thank you, Akash, for nice talk. That you stated that some QPU are two types QPU. One is related to accretion disk and the other is with corona. So how do you come to know that it is from corona? It is due to the photon from corona and it is due to the photon from accretion disk.
Sorry. So you said QPUs from different?
Yes. You said that 2.2 Hz QPU is maybe from accretion disk and 2.6.
So this is what we see from the observation. When we fit the model, we find that the lags lesser than, for frequencies lesser than 2.2 Hertz. The QPUs originate from the corona. But now, as I said, when I finished the talk, that we are now exploring a picture. We consider both the origins, and say, okay, maybe the QPU frequencies or the oscillations, they are originating from both the places, corona and the disk, and creating some kind of resonance effect. So we are exploring that. So maybe it's not just one of the two. Maybe both the things are contributing to the oscillations. So we're exploring that.
Okay, over there.
So you talked about applying these models to neutron star X-ray binary systems where you have found very high frequency kilohertz QPU. So can you explain how your model is explaining the kilohertz QPU phenomena?
Yes, so this work by Suchishmito et al. He's almost going to submit it. I don't have the plots, but he's able to fit the RMS and lag. There were no lags, there were around 0 lags only, at around, I think, 760 Hertz of QPU. So he found it for this neutron star system, but he could fit the RMS with our model. The model was simple, saying again the same thing, that there's a corona and a truncated disk, and then there are variation in both of them with some delay. So they are able to do that.
Can you comment more about the coronal structure, if you can?
So that's the thing. In this model, as of now, we cannot say the shape or the size of the corona. We can only talk about the variations of different parameters of corona.
Thank you.
Okay. So I have one last question for you. That is in MaxEJ 1535.
Yes.
It showed very strong correlation between QPU frequency and spectral index.
So we want this.
How do you incorporate that in your model?
So we found the same kind of correlation and then one more correlation. And so we couldn't say anything about that correlation, how our model can explain like how the QPU frequency are related to the specular index. But I think that paper also talks about that specular index is also related to the flux, the changes in the flux. So maybe we can say that the flux changes are different for frequencies lesser than 2.2 Hertz and greater than that. And again, it will then correspond to the amount of variations in corona and amount of variation in the truncated disk. Maybe we can, but we don't say anything about the correlation.
All right. Thank you. So let's thank Akash and let's thank all the speakers in the session.